Welcome to This Explainer. Today, we're going to unpack the absolute critical mechanism that prevents modern distributed architectures from just entirely collapsing under their own weight. When the software industry shifted away from massive, monolithic applications to these highly decoupled microservices, we essentially made a trade. We traded those localized, fairly easy to debug issues for massive, systemic, distributed failures. So if you've ever wondered exactly how the world's largest platforms survive these huge, unexpected traffic spikes without simply melting down, well, you are in the right place. We're going to explore the physics of network resilience, the real-world mechanics of distributed load, and the ultimate safety valve that literally keeps the modern web running. It's a little thing called backpressure.
30,000. Let that sink in for a second. In environments like Uber's, a single ride-hailing request from a user's phone can traverse roughly 500 discrete microservices. That one simple user action initiates this massive fan-out effect, triggering over 30,000 remote procedure calls across the network. Think about the sheer scale of that interconnection, right? And the incredibly deep dependency trees it creates. When an architecture is that deep, an anomaly at the very bottom of the stack, it doesn't just stay there. A sudden latency spike in some low-tier database will bubble up, locking up resources layer by layer until it completely tears down the entire request at the user-facing edge. So understanding how to manage this scale isn't just about writing faster code anymore. It's about managing emergent systemic properties. It's understanding that a failure anywhere is a threat everywhere.
All right, here's our roadmap. We're going to quickly look at the distributed overload problem, define what system backpressure actually is, explore the trade-offs of buffering, dropping, and slowing, dive into some real-world Kafka examples, and finally, wrap up with some rock-solid architectural best practices. Let's jump right into part one, the distributed overload problem, or as I like to think of it, the physics of distributed traffic. Let's talk about the dreaded retry storm. Think of this as the distributed system's equivalent of a thundering herd. Let's look at the math behind this kind of localized failure because it's pretty wild. Imagine you have a minor, super temporary database blip in just one service. The client calling that service doesn't get a response before its timeout window closes, right? So what does it do? It retries. But if that service is a dependency for, say, 3 upstream clients, and they all have aggressive retry logic, like 3 attempts each, you suddenly have 9 times the normal traffic hitting a database that is already struggling to stay afloat. And it gets worse. The clients of those clients also start timing out and retrying. So what starts as a tiny degradation becomes this exponential decay of system health. Your already overloaded services are now forced to handle their baseline incoming traffic on top of a massive, mathematically compounding surge in retry traffic. It is a textbook recipe for a catastrophic, cascading outage. Moving right along to part 2, defining system backpressure, which is really the cure for these cascading failures. To actually fix this overload problem, we can't just rely on scaling up hardware infinitely. That's impossible. And we definitely can't rely on passive failure. What we need is active signaling. Backpressure acts as this absolutely critical communication valve. Now, this isn't exactly a brand new concept. TCP sliding windows have used network-level backpressure for decades to stop fast senders from totally overwhelming slow receivers. But in a modern event-driven system, when a consumer experiences high load and starts falling behind, it has to actively communicate that state back up the chain to the producer. Without this two-way communication, the producer effectively blinds the consumer with a fire hose of data, exhausting its memory and compute power. By explicitly signaling the producer to slow down or pause, backpressure guarantees the system never exceeds its processing capacity. That's how you prevent those exponential retry storms and keep your throughput completely stable. I absolutely love this analogy from an Uber engineer because it beautifully captures the day-to-day realities of operating at massive scale. Think about it. If a traditional factory line gets overwhelmed, a floor manager can just hit a big red button, stop the conveyor belt, and fix the jam. But a large distributed system, it's much more like a large hospital. You can't just stop taking live production traffic when the pressure spikes. It's like a huge influx of patients suddenly hitting an emergency room. The system requires immediate triage. Anomaly detection acts kind of like the triage nurse here, routing non-critical background traffic to a waiting room while making sure the trauma center stays open for critical core services. As you add more and more microservices to your architecture, assuming the system will just magically heal itself is a total fallacy. It needs continuous care, constant validation, and built-in mechanisms to literally push back when that waiting room gets completely full.
All right, part 3, buffering, dropping, and slowing. Let's get into the actual nitty-gritty mechanics of handling this load.
When your consumers inevitably fall behind those rapid producers, your architecture has to dictate exactly what to do with that excess data. And basically, you have three core strategies here, and every single one comes with some pretty profound engineering trade-offs. First up is buffering, essentially putting data into a queue. Now, this seems safe at first glance, but unbounded queues are exactly where latency goes to hide. If you leave them unchecked, the queue just grows and grows until you hit an out-of-memory or OOM error, bringing the whole node down. Second is dropping, which is often called load shedding. Here you actively reject incoming events. Yes, you lose data, but you maintain strict operational stability and low latency. For a telemetry or metrics pipeline, totally acceptable trade-off. For a financial payments gateway, absolutely catastrophic. And third is slowing. This is true backpressure. You actively throttle the producer. The producer doesn't waste resources creating redundant events, which is great, but pulling this off requires highly complex reactive frameworks. Think RxJava or Project Reactor, so the thread isn't just blocked but efficiently yielded back to the system. Which brings us to part 4, Kafka and streaming examples. Let's look at flow control in event-driven architectures. If you operate Apache Kafka, you are probably intimately and painfully familiar with consumer lag explosion. Think about the last time a pager went off at 2 a.m. because downstream applications were totally starved for data. Often, the root cause isn't even a massive spike in user traffic. Actually, it's a structural behavior known as the stop-the-world effect, which happens during consumer group rebalancing. See, when a consumer node joins or crashes out of a group, Kafka triggers a rebalance to redistribute the workload. In older default configurations, all consumers drop their current partition assignments while the group leader figures out the new map. During this window, all processing halts entirely. Your producers are still happily firing away, but consumption drops to absolute zero, causing your lag to skyrocket artificially. So, how do we solve this and truly optimize these high-throughput pipelines? Well, engineers have to apply something called mechanical sympathy, tuning the software so it actually respects the physical hardware realities. First, implement the cooperative sticky assigner to fix that stop-the-world problem. It only revokes partitions that actually need to migrate, so the rest of the group keeps processing data without a hiccup. Over on the producer side, network I/O is almost always your bottleneck. By tweaking a setting called linger.ms to somewhere between 10 and 100 milliseconds, you intentionally delay sending data just a tiny bit to accumulate messages. Combine that with a batch size of 32 to 64 kilobytes, and suddenly you're sending fewer, much larger payloads over the wire. This drastically cuts down on the CPU interrupt overhead for both the producer and the broker. And finally, throwing ZSD compression into the mix hits that perfect sweet spot between data compression ratio and CPU cycle cost. Finally, let's wrap up with part 5, architectural best practices. How do we design for true resilience? Let's synthesize all of this into some rigorous, hard and fast rules for your architecture. Number 1, kill or bound your queues. Unbounded queues will eventually kill your application, period. Give them a strict memory limit, enforce backpressure, and fail fast. Number 2, propagate your deadlines. If a user request has a total timeout budget of 5 seconds, you have to pass that remaining time down through every single RPC. If you don't, a 5-second downstream timeout can stack into a 20-second upstream timeout, creating this massive timeout waterfall that ruins your SLA. Number 3, implement idempotency. Systems like SQS or Kafka guarantee at least once delivery. That means duplicate messages aren't a bug, they're a mathematical certainty. Your consumers must be able to process the exact same message twice without, say, double charging a customer's credit card. Number 4, separate your thread pools. You've got to isolate workloads so a slow, heavy database report doesn't consume all the threads needed for lightweight critical things like user logins. And lastly, make your retries smart. Use exponential backoff, strictly cap the maximum attempts, and inject random jitter. That jitter slightly randomizes the retry timing, ensuring your recovering services don't immediately get hammered by an aggressively synchronized thundering herd. So, I want to leave you with a bit of a provocative thought experiment. Imagine a massive marketing campaign went completely viral right this second, and your baseline traffic spiked by 10x. Do you know exactly which microservice would fall over first? Unmanaged queues are basically ticking time bombs buried deep inside your architecture. Please don't just assume your system can handle the load just because it happens to be running fine today. Look closely at your dependencies, trace those RPCs, and hunt down those unbounded buffers. By bounding them and setting up true system backpressure today, you stop the architecture from simply deciding to drop everything on its own tomorrow. Thank you so much for joining me for this explainer.